Okay, if I want a 99% confidence interval, later on when you look at your Z table, you're going to notice that it's going to be 2.58. You guys can check that for me later on. So notice, if you want to be more confident that you have the true population mean within these two numbers that you predict, in order to increase your level of confidence, you have to make the interval wider. And the interval becomes wider because the z-score that you're using to represent that range gets bigger. You're multiplying by the standard error by a bigger and bigger number, the bigger the level of confidence that you want to have about being right about it. Okay, so I'm going to leave the other parts of these problems, the other part of that problem, which is basically just repeating what we just did, except using the FEV1. I'm going to leave that up to you guys. Let's take a look at this next one. Data set low birth weight contains, I posted this on Blackboard also, so you can get to the data set as well, in case you don't have the CD. The data set low birth weight contains information recorded for a sample of 100 low birth weight infants born in 2 teaching hospitals in Boston, Massachusetts. The measurement of systolic blood pressures are saved under the variable name SBT, systolic blood pressure, while indicators of gender, where 1 represents male and 0 represents females, are saved under sex. Compute a 95% confidence interval for the true mean systolic blood pressure of male low birth weight infants. Okay, it only explains about male in Part A. Calculate 95% confidence interval for female low birth weights. Okay, so might as well do both at the same time. Do you think it's possible that males and females have the same systolic blood pressure? Okay, or another way of saying that, do you think they have different systolic blood pressures, average systolic blood pressures? Okay, and then they want you to explain it. So I'm going to actually, since you're going to actually have to do it for yourself to cut and paste the tables and stuff like that, I'm not going to change any numbers and so on and so forth. I'm just going to open this file in SPSS and take a look at what we wind up getting. I'm going to move this out of the way for now. Okay, and I'm going to open that file in SPSS. Now, if you're working with R, you're going to be basically doing the same thing, except you're going to be using the correct. You're going to be opening the file in R, and you're going to be as a CSV, comma delimited file, and you're going to be using the commands in R that you need to find the mean and the standard deviation of the sample, and to calculate the 95% confidence interval. So here is our file, right? And let's see if here's systolic blood pressure. Here's gender, male or female. If you look, this has actually been coded. If I go to the variable view, you'll see that they've already put in for you that for gender, for sex, right, the values are 0 equals male, 1 equals 0 equals female, 1 equals male. So the numbers that are back here behind this, I'm going to go to the data view again. The numbers, if I turn off the value labels, it actually shows me the numbers behind. I'll turn them back on just because it's easier to read that way. You saw that 1 represented male, and so on and so forth. So now I want to analyze this data. And as I usually do in SPSS when I want to do analysis, I start off just simply by going to Analyze. We're talking about descriptive statistics, means, standard deviation, standard errors, so on and so forth. So I'm going to go to descriptive statistics. My first 3 choices represent frequencies, counts, how many males are there, how many females are. Not really what we're being asked here, right? Descriptive statistics, well, mean, standard deviation, and so on and so forth. But usually that means look at the data as one block, combine males and females into one group. If I really want to separate males and females, and I want to find some more extensive statistics, I have to go into Explore. I'm going to click Explore. Explore brings up a box where I can tell it what's the dependence list, what's the value. Remember, it's always going to be numerical data that goes in here because we're looking for descriptive statistics like means and so on and so forth. Means really don't mean much when you look at nominal data, like names of states. The mean average name of a state is meaningless, right? So we're only looking at numerical data. In this case, the numerical data we're interested in is the blood pressures. What's the average blood pressure? Now we want to, in Explore, divide that up into males and females. Split it up into males and females. Another word for splitting something up is to factor it. Okay, so I want to factor it by gender. So I'm going to move that in there. I'm going to click on statistics. These are my options here. I have in these little boxes here. I'm going to click on statistics, and it's already going to calculate my descriptive statistics. That's checked off. Notice I can choose what I want my confidence interval to be. It defaults to 95%. If the problem it asked us 99%, I could change that 95 to a 99% right here if I wanted to. I'm just going to click continue. That's okay. If I want to develop some plots like a histogram, it's always going to give me a box plot. I can check off stem and leaf, histogram. Maybe I don't want stem and leaf. Maybe I want histogram. Okay, it's automatically always going to give me a box plot. Options are options on missing data and so on and so forth. I'm going to ignore that for the moment. I don't think there's any missing data in this data set. Down here, you can ask it, oh, give me I'm only interested in the statistics this time around, or I'm only interested in the plots this time around. You can tell it to do that, or you can tell it to do both. Okay, so I'm going to click OK. It's going to go to the output window. Now notice on the output window, first thing you get is the syntax, the commands that you could have given SPSS individually by typing them in, that would very much like using R, except that this is a language specific to SPSS, okay, that you could use to tell it, well, this is the file, get file, and that's the file you open, low birth weight, and it happens to be on my desktop. Data set name, and get, we repeated it twice. Data set name, examine the variables, systolic blood pressure, factored by sex, and now plot the box plot, compare the groups, give me statistics, descriptive statistics, calculate the 95% confidence interval. This is how you deal with the missing values. I left it at the default, and so on and so forth. So this describes what we just did by using the drop menus. And in R, you guys that are working with R know that you would use kind of a similar syntax, right? Not the same thing exactly, but a similar syntax. Okay, so what do we wind up with? We wind up with finding out that the mean systolic blood pressure for female infants is 46.46. The mean for males is 47.86. Based on this sample, which is a pretty big sample, 100, right? It looks like the systolic blood pressure for male infants is greater than the systolic blood pressure for female infants. We don't really have a handle yet on if we can say they're really different, because we don't know how accurate that, how variable these values were. How likely it would be that if we took another 100 infants, that we wouldn't get the reverse outcome, right? So that's where our confidence interval helps us. In this case, our 95% confidence interval for female systolic blood pressure is 43.5 to 49.5. So we're 95% sure the true population mean for all females is between 43.5 and 49.5. We're 95% sure that the mean systolic blood pressure for all male infants is between 44.27 and 41.5. I'm going to take that and I'm going to put that on a number scale back here on my little table here. Let me see how easily I can do this. Okay, so for female infants, let me get this out of the way and get to the output. For female infants, I can't get this in the window at the same time. For female infants, it was 43.5. I'm going to round it a little bit, make it easy on myself. 49.5 to 49.5. 43.5 to 49.5. So that's going to be, that's going to be 43.5 to 49.5. I'm 95% certain that the true female systolic blood pressure for these infants, this population of infants, is between these two numbers. Well, how about male? Male, I am 95% sure for males that it's between 44 and a quarter So 44.25 would be here, and 49, where is it? 51.45. 51.45. Let's take a look at that. Well, gee, these overlap quite a bit, right? I can't really tell for sure based on this sample that these two are different. Let me put it from another perspective. What if I were, if I knew that uh, 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 female infants had a blood pressure between 30 and 45. I took everyone in the country and had a blood pressure between 30 and 45, right? And then I took male infants and took everyone in the country, the whole population, and found that it had the males had blood pressure 47 to 62. Well, I know that they're different because not a single one of these values overlaps. So females are always lower blood pressure than males. Of course, in reality, that never happens. In fact, the range for females might be 30 to 63, and the range for males might be 31 to uh, uh, 67, and so on and so forth. The real question here is, can I tell with any certainty whether the mean for females in the population is different than the mean for males in the population? That's really the key, right? So in this case, in order to be able to say with 95% certainty that the mean systolic blood pressure for females in the population and males in the population is different, I have to have confidence intervals that don't overlap. The actual values can overlap, but my mean and my confidence interval for my means can't overlap. In other words, I need to be 95% sure that the mean for females is, let's say, 43 to 47, and the mean for males, right, is 48 to 52, right? The mean's going to be there. If I'm 95% sure that this is the range for females, and I'm 95% sure that this is the range for males, if they don't overlap with each other, I can say I'm 95% sure that the means for females is not equal to the means for males. If they overlap, there's a possibility that the mean for males could be the same as the mean for females, okay, at that level of certainty, right? So if I wanted to, there's a couple of things. If they do overlap, what can I do to try and determine if they really are different, or prove that they're really different with a level of certainty? One thing you do is like lower your tolerance for error. If it's 90%, you can make this range narrower and this range narrower. So maybe they won't overlap anymore. Or I could take my sample size and make it bigger, which makes my standard error smaller, which makes my range for confidence interval smaller. So that'll narrow them also. Maybe I'll be able to distinguish them. But you get what I'm saying? In other words, you got to make sure those confidence intervals don't overlap. Okay. So this is kind of like, I'm sure for many of you, kind of a new concept, right? But I'm hoping that if we repeat it a few times, you look at it in different circumstances and stuff like that, that it will make sense to you how we use this confidence interval to determine whether we have the same means or different means. Okay, so that's what really we're looking for, is whether these confidence intervals in these groups that we're looking at overlap. Okay, so I'm going to leave it up to you to, cut and paste this and so on and so forth, come up with your own description and answer for the questions and so on. So again, I've uploaded all the data files and so on and so forth. Let me just take a quick look as we're running down on time. Let's get a quick look at that. I think there's one more problem. Do we have one more problem? This one was chapter. Oh, we have a couple more problems, right? No, I'm wrong. This one was, which problem was this? Populate. Okay, nope. We were still on chapter. That was number 13. Yep, that was number 13. I think that's the only one that actually used a data set from the textbook. You can always let me know if I'm wrong about this. Let's take a look at this chapter 14, how we would approach that. Suppose you select a random sample of 40 children, population of newborn infants in Mexico. The probability that a child in this population weighs at most 2,500 grams is 0.15. Okay, so what they've told us is you got a population, 40 children. The probability a child in this population weighs at most 2,500 grams is 0.15. For a sample of size 40, what is the probability that 4 or fewer of the infants weigh at most 2,500 grams? Compute the I'm gonna come back to this. I'm gonna do the next problem first. I got a reason for this. In a New York City study, evaluate whether there's available time of birth used to identify children with special education needs. Random sample of 45 third graders enrolled in special education programs at public school system. 4 have mothers who have had more than 12 years of schooling. Okay, out of 45, only 4 have mothers who have 12 years of schooling. Construct a 90% confidence interval for the population proportion of children with special education needs whose mothers have had more than 12 years of schooling. Okay, now remember what the formula that we used for approximating the distribution of a proportion. Okay, anybody remember what that formula was? Oops. Let's see. I said to myself, let me see if I can't get another piece of paper up here to work with. Let's see. Let me close this. Oops. Should have said yes. Nope. Let me go back to notebook. Here we go. Let me get a fresh page. Okay. So 4, if I remember correctly, 4 out of 45 mothers had more than 12 years of education. Okay, 4 out of 45. So in our sample, our proportion of mothers that had more than 12 years of education is 4 out of 45. Okay, that's our sample. So now our standard, what is that represents? Let's see what that value is. It's going to be about 10%, right? So I'm going to actually calculate it. 0.45. Oops. Cancel. 4 divided by 45 equals 0.89. Okay, I'm going to round that to 0.09. When you do your homework, you can use 0.089 preferably. Okay, so it's equal to 0.9. Okay, so now if I were to take repeated samples of size 45, if I did that over and over again, what would be the standard deviation for those repeated samples, or in other words, kind of a standard error? Well, my standard error is going to be equal to P times 1 minus P over N, right? I'm going to take that whole thing and take the square root of it. What's that going to be equal to? It's going to be equal to 0.09. 1 minus P is going to be 0.91, right? Divided by my sample size, which is N. I'm going to take the square root of that. So the distribution of those samples, repeated samples, is going to be, let's see, 0.09 times 0.91 divided by N, which is 45, equals that, and I'm going to take the square root of that. Notice it's a small fraction, but when you're working with proportions, when I take the square root of that, the number multiplied by itself will give us that number. It's actually a bigger number. Okay, it's going to be 0.042. Okay, I'm going to call that 0.04 to simplify our calculations. You keep that extra digit though. It's equal to 0.04. That's my standard error. if I'm predicting that if I take repeated samples from these of size 45 from women in this population, children who are in special ed, mothers of women in special ed, on the average, I'd get a proportion of 0.09. But my standard error, my distribution, would represent a spread of 0.04. I can use this normal distribution as an approximation of what we were working with before, which was the binomial distribution. Remember the binomial distribution, where I would take this proportion and I would use it to say, well, what's the probability that if I took 45, a sample of 45 mothers, that 3 of them would have more than 12 years of education, or 5 or more, or exactly 4, and so on and so forth. Remember that binomial distribution calculation we did before? In this case, I'm using this to estimate how this binomial outcome is distributed. Okay, so now let's take a look at the question that they're asking us that we're going to base our answer on. And that is, construct a 90% confidence interval for the population proportion of children with special education needs whose mothers have more than 12 years. So we want a 90% confidence interval. So I'm going to look at question A, 90% confidence interval. Well, we know the way we calculate a confidence interval when we're using means is the mean, right? X bar plus or minus whatever number for 90% confidence. Anybody remember 90% confidence interval? What number I'm using here for the z-score? I'm using 1.64. Had it been they asked for a 95% confidence interval, it would have been 1.96. Had it been a 99% confidence interval, it would have been 2.58. Okay, 1.64 in this case because 90% times the standard error. In this case, I'm working with a proportion. So instead, I'm looking at P plus or minus 1.64 times the standard error, which is 0.04, right? So what is, let's see, my average is 0.09 plus or minus 1.64. 1.64 times 0.04 equals let's see, that looks like about 7%, about 6.5%. I'm going to call it 6.5% for our 6.6%, right? So I'm looking at our confidence interval being plus or minus 0.06. I forget what it was. I'm going to call it 6. I'm going to call it 6.6. 0.09 plus or minus 0.06. Right, so my 95% confidence interval for the true proportion of mothers in this population that have more than 12 years of education, mothers of children in special ed, is going to be somewhere between 0.04, and I'm going to add this to it, and 0.15, somewhere between 4% and 15%. You guys, thank you, Rebecca, again. At least I know one of you guys is awake. Okay, thanks, Rebecca. I don't mean to chide you guys too much, but it's nice if I get some, every once in a while, if you give me a little bit of feedback so I know if I'm losing you or if you guys are keeping up with me. So if you can, I know that a lot of times I'm doing these early in the morning or late at night and stuff like that. And, it's easy to kind of phase out a little bit. So, but it really helps me if I get a little bit of feedback so I know what's going on, even if you can still hear me or not, because we're all working on the internet. So we're 95% sure that it's between those two, 90% sure we're between those two values. That's our confidence interval. Okay, we're using proportions the same way that we use the mean. We're predicting based on a sample that if this is the percentage of people that have diabetes, that have more than 12 years of education, et cetera, within this population, we can also define that rather than just as a single proportion for our sample, define it as a range and describe how much confidence that we have in our range, making it more valuable than just a guess at the population. So then next case, they go 22% and so on and so forth. Conduct a level at the test of 0.05 level of confidence. That means 0.05 level of confidence means 5% chance of error. 5% chance of error is another way of saying 95% certainty. Another way of saying 95% confidence interval. So don't let that fool you. Okay, and so on and so forth. I'll leave that up to you. I just want to go quickly back, finish up by quickly going back, take a look at problem number 5. Suppose you select a random sample of 40 children population of newborn infants in Mexico. Probability a child in this population weighs at most 2,500 grams. You know, they kind of like threw us a little bit of a curve there. In the second part of this, they say using what they're saying is the probability that a child weighs at most 2,500 grams. In other words, weighs 2,500 grams or less, or is underweight at birth, right? They're saying what's the probability it's underweight at birth? Probability is 0.15. P of being underweight at birth is 0.15. For a sample size of 40, what is the probability that 4 or fewer of the infants weigh 25 at most 2,500 grams? Okay, so we have a sample probability that 4 or fewer out of 40. In other words, what's the probability that 10%, 4 or fewer, right, would be the proportion of this distribution that's below a samples below that it was probability that these would occur out of the 40 people, that this would occur 4 times out of a sample size of 40. Okay, so now it's also a random size of 40 that we're talking about. Well, what are we saying there? Okay, so we know the probability of getting our probability is 0.15. What's the probability that if this distribution is 0.15, what's the probability that we'd get exactly 4 children out of 40? Well, that's going to be our binomial distribution. Okay, what's the probability using normal distribution estimate probability for a future? Okay, well, in this case, they're saying that you take a sample size of 40. What's the probability, given that this occurs 15% of the time, what's the probability that 4 or fewer infants weigh at most 2,500 grams? Well, 15% of 40 is, let's see, 10% of 40 is 4 children. 15% of 40 happens to be 6 children. So our expectation is most of the time, most likely outcome, if we take a sample of 40 children, we're going to find 6 of them. In other words, the sample size times the probability, n times p, that's going to most likely outcome. It's going to be 6 children. We did this before when we were talking about binomial distribution. They are asking what's the probability that if you took a sample, given this population, that you took a sample of 40 children, that only 4 or fewer were underweight. Okay, that's binomial distribution. Say in part A, they threw us a little bit of a curve. So I'm going to bring up Excel because that's the easiest way for me to do a binomial distribution. Okay, and I'm going to make this big. Data, let's see if I can make this bigger so we can see it. Okay, so now let's see what I got here. I'm going to use a binomial distribution. Equal binom dist parentheses. It prompts me for the numbers that I'm looking for the numbers that it needs to do the calculation. It asks me for the number of successes. That's the number of children that are a low birth weight. The number of trials. That's the size of our sample. The probability of any individual child being low birth weight, and whether I want a cumulative probability or a probability for exactly that outcome. Okay, so let's see what this is in this case. The number of successes, where we're saying, what's the probability of getting 4 or fewer? Well, number of successes then is 4, comma. The number of trials is the sample size, which is, they told us for part A is 40, sampled 40 children. The probability that any particular child is underweight, well, that's 15%, 0.15, comma, and now I have to decide whether to say true or false for cumulative. Well, if they said, what's the probability that exactly 4 children out of those 40 that you choose randomly are 2,500 grams or less, then I would put false for cumulative, because I don't want it to add up. I want it to just be exact number. But they say probability of 4 or fewer. So I want the probability for 4, that it could be 4 or 3 or 2 or 1 or 0 out of 40, right? So I want to say true for cumulative. So the probability based on the binomial distribution that we would get an outcome if we randomly sampled 40 children from this population, given what we know about it from the first part of the description of problem 5, probability that we get that low an outcome would be about 26%, right? About 1 in 4 times we'd get 4 or fewer. And then 74% of the time we get 5 or more, obviously, since the probability's got to add up to 100%. Okay, so now let's look at this from another perspective. Using the normal approximation to the binomial distribution, estimate the probability that 4 or fewer of the children weigh at most 2,500 grams. Well, now this time we want to know what's the probability that we'll get an outcome where using the normal approximation that we used before, that we'd get the same result. Okay, so now I'm gonna need to move something a little bit, right? That's why I want to do this one second, because a little that asking about the binomial distribution changed things a little bit. So let's take a look at this. Our sample size is 40, right? Our probability that a child would be underweight is 0.15, 15%. I'll put a 0 in front of it to keep it clear. And we want to know what's the likelihood, if we took repeated samples of size 40, what's the probability that we would wind up with a sample mean that is less than, fewer than 4 children. Okay, well, 4 children is a probability of 10% out of 40, 0.10. What's the probability that if we took from this population, 0.15, what's the probability we get a result of children that get a result where only 10% of those 40 children are underweight? Okay, well, in order to predict the likelihood of getting a proportion in this, instead of a mean for a sample, a proportion for a sample that's less than 10%, 4 out of 40, right? 4 or fewer, right? Of getting less than 10% of children that are underweight when I took my sample of 40. In order to predict that, I need to know what this, I know that I'm expecting 0.15 on the average, so half the time less than, half the time more than that. In order to predict that, I need to know how spread out this is. So I need to know what the standard deviation for all of these proportions, in a sense, is more like a standard error, right? I need to know what that is. And how do I predict that again? Remember, this is an approximation of the binomial distribution. The way we do that again was the square root of p times 1 minus p, right? Divided by n. Okay, and that in our case is going to be the square root of 0.15 times 0.85 divided by the sample size, which is 40. So that's going to be equal to, let's see, 0.15 times 0.85, right? That's going to be equal to that, divided by 40. Going to be equal to that. And then I got to take square root. It's going to be equal to about 0.056. Okay, I'm going to call it 0.06 for my purposes. Okay, I'll call it 0.06. Okay, so what's the probability, given that that's my standard error, what's the probability that I would get a result less than 0.01? Well, how many standard deviations below the mean am I if I have a result of 0.10? Well, let's see, my z-score, it's normal distribution. By the way, in order for us to assume this is normally distributed and we can use this approximation, we want our sample size to be greater than 30. Again, just like everything else. So z is going to be equal to the value I'm interested in, which is 0.10, minus 0.15 over my standard error of 0.06. How many standard deviations below what my expected proportion or my mean is that going to be? Well, it's going to be minus 0.05 over 0.06, or it's going to be minus point, what is that? What's 1/6? What's 5/6? 5 divided by 6. Oh, it's 0.83 minus 0.83. So now I go to my standard normal distribution table and I look up what area is represented by the area below a z-score of minus 0.83. And if I go to the table that I have handy right now, which is, do I still have it open? I might have closed it, eh? Let me go back to here and I'll finish up with this. I'm going to use the aggressivity because it's got negative numbers in it. Okay, let's see. Negative 0.8, negative 0.081012, about 20%. The area to the left of this distribution. Remember, if you use the other table, you gotta consider what area it's defining. The area to the left of that z-score is about 20%. So the probability that I get an outcome that's less than 10%, or less than 4 children out of 40, is about 20% at a time. Okay, what was the number that I got when I used the binomial distribution? Anybody remember what that number was? How does that compare to what I got when I calculated it this way? I rounded, so it's a little bit more error, right? What was it before? It was, I don't remember what it was. Anybody remember what it was? Is it up here somewhere? Oh, it was on, oh, it's in my Excel spreadsheet. Let's see if I still got that open. It was, I predicted it was 26%, right? So I didn't get exactly the same number. I might have gotten a better estimation if I had calculated this a little bit more carefully. Did I round anything? I didn't really round anything, did I? So I got as I expected, a normal approximation of the binomial distribution. I didn't get exactly the same answer, but I got a pretty close answer for this. So this can be a little confusing, but let's make this a start on the explanation of this. And as time goes on, we'll fill in some more details. Does that sound, you guys basically get the idea of what I did there? How I was able to calculate this likelihood two ways. Normal distribution, using the binomial distribution as we did it before, and now using the normal approximation to the binomial distribution. So if you had to now, can you go back and at least go through those steps, even if it sounds a little cloudy to you? Okay, I think so, right? We can at least get through the homework on it. And then as time goes on, it'll get even clearer and clearer. It sure is a little tricky, exactly. Well, that's why I'm here, right? You wouldn't need me, if they wouldn't be paying me the big bucks if it wasn't tricky, right? So hopefully this will help out. And if the recording encodes properly, I'll post this so you can go back and look at it again. Okay, but we changed a few numbers and stuff like that. So I want to make sure that you still have to kind of do this on your own and so on. But you can refer back to this if you kind of get hung up on it. Give it a try on your own first, though. And then if you struggle with it, go back and play back that portion of the video and see if it helps you kickstart you on the problem and stuff like that and get you through it. Okay, so see you in class tomorrow night, or Monday night, excuse me. And hope you guys can get through the homework with this little bit of a start. Take care, guys. Have a good rest of the weekend.